My name is Elisabeth Falk. Everyone calls me Lisa, so that's absolutely fine. I've been talking about the neutrino, which is my favorite particle, the particle that I've been doing research on for 20 years. It's the least understood of the matter particles. And it's very quirky, and we think that it holds clues to some of the biggest questions in the universe. For example, why there is matter here and no antimatter left. So ultimately, why we are here. And that link between the biggest structures and questions and the neutrino, which is the tiniest of the matter particles, is so fascinating. And I hope that people have come away being made aware of that link and that have piqued their curiosity. If you roll back history a little bit into earlier in the 20th century, the neutrino has always been a bit of an enigma. In fact, it was thought up by Wolfgang Pauli as an explanation to a mystery that he couldn't solve in any other way, and it is to do with radioactive decay, beta decay. Beta decay is different from the other types of radioactive decay in that the electrons don't have a well-defined energy. And the only way that you can explain that is either conservation of energy doesn't hold, which would be pretty fundamental, or there has to be another particle taking away some of the energy. And he wasn't quite ready to throw out conservation of energy, so he invented the neutrino particle. But he didn't think that anyone could actually detect it because he thought it would have been seen by then. And as a scientist, that's something you can't do. You can't invent a hypothesis that can't be verified or refuted. So he wrote a letter apologizing for having come up with this idea. And then it actually took 25 years before experimentalists could detect the neutrino, and it was with neutrinos from a nuclear power plant in much the same way as we're going to look at nuclear reactor neutrinos today. In fact, the detection mechanism is the same. And Pauli had promised that if anyone ever sees this particle, I will give them a case of champagne. And he stood by his word a quarter of a century later. So it has always been right on the edge of what people felt comfortable believing, if you see it. Lovely to see so many faces here. I am going to share with you what I do for a living when you don't see me as a teacher. First of all, what's happening in here? All right, while we're sitting here, you're listening, and I'm talking, there are 100 trillion neutrinos passing through each one of our bodies in here, every second. Now, 100 trillion, that's 1 followed by 14 zeros. So that's a pretty big number every single second. And because I'm a teacher and there's no let up, so I'm going to set you a little assignment to think about while I talk to you about neutrinos. In your lifetime, how many of these neutrinos do you think are going to interact with an atom in your body? Right. So that's for you to think about, and I'll come back to it at the end. Now, where do all these neutrinos come from? Most of them, here on Earth, come from our nearest star, the Sun. The Sun produces an enormous amount of neutrinos as part of the fusion processes that go on inside the Sun. And because we're on a cosmological scale, we're very near the Sun, most of the neutrinos that go through you and me, that's where they come from. But neutrinos are created in lots of other places in the universe as well. For example, they are created when a star dies and goes up in a bang in a supernova. And lots of them are also created at the very start of the Big Bang, and they're still floating around in the universe. When cosmic rays strike the atmosphere of the Earth, you get quite violent collisions on a microscopic scale, and neutrinos are produced in those collisions as well. So we actually have neutrinos being rained on us from those cosmic rays as well. And then on a more local scale, neutrinos are also produced in radioactive processes, and they can take place, for example, in man-made places of radioactivity, such as a nuclear power plant, but they also happen spontaneously in our planet, in the Earth. That is the source of geothermal heat in our planet. So there's lots of radioactivity going on under our feet as well. Now, neutrinos, they are pretty strange creatures. To begin with, there are 3 of them. That's maybe not so strange. If you're familiar with the building blocks of matter, you might know that the atoms that we're made up of, they are made up of neutrons and protons, which in turn are made of 2 types of quark. They're the up and down quarks, the U and D, in the top left corner of that little table. And around the nucleus of an atom, you have electrons spinning around. And there's one type of neutrino called electron neutrino, which is the body of the electron. And then there are 2 more families of particles that are sort of partners to each one of the 4 particles in the leftmost column. They're not present in ordinary matter because they can simply decay into the lighter ones. But they are there and part of the symmetry of our building blocks of matter. So for each one of those other 2 families, there is also a neutrino called the muon neutrino. That's the one in the middle. And the tau neutrino is the one on the right. Okay, so we have 3 neutrinos. So far, so good. Now, they are very different from the other matter particles. So for a start, all the quarks and the electrons and the bodies, they have electric charge. The neutrino does not. It is electrically neutral. So you can't make electricity with it, and it doesn't know about the electromagnetic force. Also, the neutrino is very light. Of the normal particles that we know about and sort of meet implicitly in our everyday matter, the quarks and the electrons are many times more heavy than the neutrino. In fact, the neutrino is about 10 million times lighter than the neutrino, which is the lightest one of the other guys. So that's quite a lot lighter. And we don't really know why this is so. It's quite a long way off the other particles. Right. Also, they travel. They spend their lives traveling around in space. They stop for very little, and they travel very nearly at the speed of light. Not quite, but almost. So that's what they do. If you create one, it will always travel, and it will spend the rest of its days traveling through space. In fact, they are quite shy neutrinos. They don't often interact with other matter. They will very occasionally, but it's very rare. And in fact, they're quite happy to travel right through planet Earth. So the neutrinos that come from the sun, they go right through you and me, they go right through the floor, and they go right through planet Earth and out on the other side, and they continue their journey through space. And in fact, it takes trillions of Earths to stop even one neutrino. The quirkiness doesn't stop there. The 3 types, in fact, they get on rather well with each other, so well that they're quite happy to transmute from one type to another. This is called neutrino oscillations, and it was the discovery that earned the Nobel Prize in Physics 3 years ago. Right. So they're quite happy in flight to change from one type to another. Right, so quirky neutrinos, but why do we care and why is it interesting to study them? Well, for a start, if we go back to the Big Bang, matter and antimatter were created in equal parts. You probably all know that when antimatter and matter meet each other, they are essentially the same thing, but they have opposite electric charge. And when they meet each other, they annihilate. Now, if the laws of nature had treated matter and antimatter in exactly the same way, then by now all the matter that was created at the Big Bang would have met with each one with its antiparticle, and they would have annihilated, and space would be empty. It would be full of radiation, so a bit of a glow, but no matter, no atoms, no neutrinos, no you and me, and it would be a pretty boring place. Now clearly that isn't the case. If you turn your telescope outwards, we can see that there's quite a lot of matter out there. This is the leftover from when all the rest has met and annihilated. And we don't fully know why the matter that is there is there. And it's one of the hottest topics in physics research to try and figure out. We have some partial answers, but only partial. And we think that neutrinos are probably the best candidate to hold a good chunk of the rest of the answer. Right. Now, you may recall from schoolwork radioactivity. One type of it is when a neutron inside a nucleus changes from neutron to a proton, and when it falls apart to a proton, it gives off an electron, and in fact it also gives off a neutrino, and to be precise, it's an antineutrino. Now, in general, I said the laws of nature treat matter and antimatter equally. So every time a matter particle is created, an antimatter particle is also created. So there's no net change inside the nucleus when the neutron becomes a proton, but an electron is created, and that's a matter particle, and then an antineutrino is created, and that's an antiparticle. So there's still no net change in terms of shifting the balance. Now, you can do this twice, in fact, at the same time, in the same nucleus. That's a double beta decay. It happens twice at the same time, so you have two neutrons that change into two protons, get two electrons out, and two antineutrinos. Two matter particles and two antimatter particles. So still no change. Now, we think that the neutrino is even quirkier than what I've told you so far. We think that, in fact, it may be its own antiparticle. It doesn't have any electric charge, so if you take the opposite charge, you still get a neutral particle, and in principle, the neutrino could be its own antiparticle. And what could happen then is that instead of this, you have a double beta decay with no neutrinos in it, because they annihilate. So you get two electrons out and no neutrinos. So you have in fact created two matter particles and no antimatter particles. So you have created an imbalance here. This particular type of radioactive decay is called Neutrinoless double beta decay. It's a bit of a mouthful, but that's what it's called. And that is one of the ways in which we can find out some of the answers to some of these questions about the neutrino. So, for example, we can go chasing why there is matter left over in the universe, and we can find out about, we don't know exactly what the mass of the neutrino is, but this is a process that if it does exist, it can help us with the answers to that. Now, there is a problem with this. This is an incredibly rare process. We don't know how rare exactly it is because nobody's seen it yet, but we know that it's at least the half-life. So if you take a number of atoms that can decay in this way, the time you have to wait for half of them to decay is upwards of 10 to the 26 years. Now, the age of the universe is only 10 to the 10 years, so that's quite a lot longer. Now, on the other hand, if you could find it, and you could even measure the half-life, then that will tell you something about the mass of the neutrino, because the heavier the neutrino is, the shorter the half-life. Short here in relative terms. Right? So ideally, what we would love to be able to do is to discover this process, and it would tell us that the neutrino is its own antiparticle, and it would give us insights in all of these things. And if we can see enough of these decays that we can actually measure the half-life as well, then we've got a handle on the mass of the neutrino. Right, so how would you go about doing that? Well, I'm going to take you on a little visit to our experiment. It's located in Ontario in Canada, where the pin on the map is. There is a mine, and in that mine there's a lab called Snow Lab, and in that lab, the bottom of the mine, is where our experiment is located. Now, Snow Lab is about 4 or 5 hours drive north of Toronto. And in order to get there, you have to get to Sudbury, which is the nearest town, and you have to get to the mine. And then you have to take a lift down into the mine, and you travel here in shaft number 9. And it'll take you 2 kilometers underground. So that's quite a long lift ride. It's one of the deepest mines in the world. And then you have a bit of a walk as well. When you get out to the lift, you have to walk for a mile down in one of the mine drifts. And at the end of the drift, there is a lab, that's Snow Lab. And in there is where our experiment is located. Okay, so you missed, my fault, you missed the title slide. This is what was on it. And I was going to come back to it anyway, so no harm done. This is the detector that we use to look for these neutrinos. And this is a picture taken from the inside of it. It's a big plastic bubble that you can see here, the thing that looks like a translucent ball. It is an acrylic bubble. On the inside, at the moment, there is water, and on the outside there is water as well. I'll tell you a little bit more about that in just a moment. And then you can see all these little dots around the side. They are electronic eyes called photomultiplier tubes. They're very sensitive light detectors. They can count single photons, so single particles of light. And what we will do when we're fully set up and running, chasing Neutrinoless double beta decay, then we will replace the water that's inside the bubble. In fact, we've started replacing it now with something called scintillator. It's an oil-based liquid, and when electrically charged particles travel through this oil-based liquid, they give off some of their energy, and that creates little glows of light in the scintillator. And these electronic eyes around it can pick up those light signals, and that's how we detect that something is happening. There are about 10,000 of these photomultiplier tubes sitting around the detector. Okay, so far so good, but replacing the water on the inside with this liquid scintillator isn't going to do the experiment for us, because we need something that can potentially undergo this radioactive decay called Neutrinoless double beta decay as well. So we need something more. We need some element that has the potential to do double beta decay. And we have picked an element called tellurium. It is a metal, and you typically get it as a byproduct in gold mining. So it's sort of an unwanted thing you get if you're into gold mining. It is used in semiconductors and electronics and mobile phones and in solar cells, for example. So there's been a bit of an upswing in the market for tellurium in recent years. Now what we're going to do when we're ready, we've already bought loads of tellurium and it's sitting in the mine. And once we've got this oil-based scintillator in, then we're going to dissolve several tons of tellurium in there. And then we're going to sit and watch and wait and see if we get any radioactive decays from the tellurium. As you probably guessed, neutrino physicists learn to be pretty patient people, right? Especially if the half-life is 10 to 26 years or longer. Now, of course, we're going to put in more than just a few atoms. We're going to put in tons and tons of tellurium. But even so, and waiting for 5-10 years, at best, we can still only hope to detect a handful of these radioactive decays. So we're talking maybe 5, 10, if we're lucky. Right? So even with this big detector and tons of tellurium and lots of patience, said if the ultimate result is going to be something of the order of 10 neutrinos maybe, or 10 radioactive decays, I should say, then clearly there are going to be some challenges here. Now, one of the challenges, if I step back for a second here, is actually on the way in. Now, this is an active mine, a nickel mine. Mines are not particularly clean, right? Everything around us, you and me, and building materials, and the bedrock there, which is granite, is radioactive, and there's a lot of dust in a mine, and it's easy for that dust to get in. If we get as much as even a gram of mine dust into our experiment, then that's our experiment done and dusted and over with. So everything has to be super duper clean. So this lab at the end of the mine drift is actually a clean room facility operating at the highest standard of clean room that you can get. That means that at the entrance door to the lab, there is a bit of a transition because you have to wear mine gear to get to the entrance door. Traveling down, you wear mine coveralls, mine boots, a hard hat, headlight, and all of these things. And you walk through the mine drift and you get sweaty, and because it's almost 30 degrees down there, 2 kilometers underground, and it's dusty and filthy. So by the time you get there, you actually have to strip off completely, have a shower, have a hair wash. You can only use the unperfumed soap and shampoo that is there, provided in the shower at the lab. You can bring your own underwear, but that's pretty much it. Everything else is washed and clean, and you borrow it from the clean side of the lab. So you get lab coveralls, a hairnet, a clean hard hat, clean socks, clean lab shoes that stay in the lab, and gloves. And as you get nearer to where we're actually working with the experiment, you have to take an air shower. So you have to step into a shower cubicle, but instead of water, they basically shower you down with air in case you picked up any dust. And when you get nearer still, you have to change your boots again, and you have to put gloves on, and so on. And every piece of detector material that gets anywhere near there, or electronics or computers, has to be scrupulously cleaned before it can get anywhere near the experiment. So it's a bit of a palaver to get down there. And once you're down, you stay down for a whole day. And you travel back up when the mine workers finish their day. So there are some logistics challenges with doing an experiment this way. You probably wonder, but why are we at the bottom of a mine then? Whether radioactive mine walls, the granite and so on. Well, those cosmic rays that I told you about at the beginning, some of the particles in those showers can actually penetrate quite deep. But the deeper you go, the less of it you get. So that's one of the reasons we go in there, because some of those particles that are not neutrinos from there are electrically charged, and they will cause background noise in our detector. So we go as deep as we reasonably can to get rid of as much of that background as possible. And then everything is kept clean. Right? For comparison, apart from the cleaning and the palaver here, I thought I'd give you an indication of what it takes. So we're talking maybe 5-10 interesting events over a period of several years. And for comparison, if you bring your lunch banana in there, a banana typically gives off about 15 radioactive decays per second. So that's a bit of a no-no. And Brazil nuts, that size, they can give up to 1 decay per second. So no food or anything else that can interfere with our measurements. So we're kind of, fighting a bit of a battle to keep everything so clean that we can see 5 or 10 events over a time scale of 5 or 10 years when you've got this going on everywhere around you. All right, well, fortunately, exciting though this is, it isn't the only thing we're doing with this experiment. There are lots of other exciting things you can do with neutrinos as well, right? So I told you at the beginning that most of the neutrinos that go through you and me, they come from the sun. And in fact, we can use those neutrinos as messengers to learn more about the sun. Originally, they were used to tell us about how the neutrinos transmute from one type to another, because inside the sun is very, very dense. So we learned a lot about how neutrinos interact with matter and how these transmutations happen when there's matter involved. These days, however, we can learn about how the fusion processes in the sun work by looking at the neutrinos that come out. And although you need to be a bit patient when the neutrinos are so shy, in many ways they're better than using the light, because a photon created inside the center of the sun, because the photon will interact much more readily with all the matter on its way out, it takes about a couple of 100,000 years for a photon to get out from the center of the sun out to the outside. So if you look at light that comes from inside the sun, it will tell us what happened a couple of 100,000 years ago in the sun. If you want to know what's happening now, you look at the neutrinos, because the neutrinos, they are quite happy to just zip right through the sun as well. And so what we see in the neutrinos is what's happening now in the sun. Okay, I mentioned that supernovae are another source of neutrinos, and in fact we can watch for supernovae to learn more about how they happen. So at the end of its lifespan, certain types of stars, when they run out of fuel to do fusion with, they collapse under their own gravity, and the outermost layers, they fall in, and then they actually bounce off the core that has already collapsed, and then that matter gets thrown out into the universe, and that's a supernova explosion. Now you may think that those things are bright in terms of how much light they send off, and in fact, when for a brief while when a supernova happens, it can outshine the galaxies in its vicinity. So you get a lot of light coming out of them, And still, that's nothing compared to how many neutrinos you get out. 99% of the energy that gets released in an explosion like this is actually in the form of neutrinos. So all that light is just a tiny, tiny fragment of all the energy that gets slung out. So if you can pick up some of those neutrinos, then you can learn something interesting about supernovae and how they happen. It has been done once before. Supernova explosions happen all the time in our universe, but if we're going to pick them up with detectors like ours, then they can't be too far away. So this particular one is called supernova 1987 because it happened in 1987, and it's got the letter A after it because it was the first one that was recorded that year in February. It took place in the Magellanic Cloud, which is our nearest galaxy neighbor to the Milky Way. We haven't seen any since. There were 3 experiments in different places on Earth when that one went off, doing neutrino physics. And between them, they picked up about 20 extra neutrinos above and beyond what they normally see within a time span of 10 seconds or so. You might think that that's not a lot if 99% of the energy from a dying star gets thrown out as neutrinos, but then you have to remember that only a small fraction of them come our way, and an even smaller fraction still will actually do anything. Most of them will go right through. But those 20 or so neutrinos, they generated more than 1,000 publications. And every single neutrino experiment that has had the ability since 1987 sits on supernova watch. And our experiment is no different. Whether we get lucky and see one while we're running, who knows? But you wouldn't want your detector to be switched off if it does happen, right? So we're all watching. Okay, and here's another thing you can do. So I also mentioned that some of the neutrinos going through UNA, they actually come from underneath. They come from inside our own Earth. So radioactive decays take place in the crust of the Earth. So in the granite, in the bedrock, for example. But even more so, it happens in the mantle. And in fact, those radioactive decays are what the heat that is generated from those radioactive decays is what drives the motion of the tectonic plates. So it's quite interesting from a geological point of view to figure out where the neutrinos are, because they tell us where the radioactivity is happening, and that tells us where certain minerals are and how the mantle is moving around, the currents in the mantle. Right? So what you want to do, if you can, is to monitor this neutrino glow coming out of the mantle. And that's one of the things that we do as well with SNO+, our experiment. So we're looking for neutrinos that come out of the Canadian Shield. So that's the bit of rock over northeastern Canada. You won't get many, but every single one helps us figure out what's happening underneath as well. And then finally, we still have things to learn about these neutrino oscillations. Now, we have learned quite a few things, but there are still some unanswered questions that are really important there. So they provide another route into how neutrinos could be responsible for the matter-antimatter asymmetry in the universe, for example. So to do that, you need a good neutrino beam, preferably one that humans have created in one way or another, so that you know exactly what you started with. And nuclear reactors are actually a good source for that. You can make them in particle accelerators as well, but you don't have to. You can use nuclear power plants if you have some. And we happen to have 3 big nuclear power plants between Toronto and Sudbury, where our experiment is. So we look out for neutrinos that come from these power plants as well, and we'll be contributing to learning more about neutrino oscillations. Okay, I promised to come back to this question about how many neutrinos interact in your body in your lifetime. So with 100 trillion of them going through each of you every second, how many do you think will actually interact in your body in your lifetime? Yeah? None? Any other guesses? It's actually a very close guess. On average, about 1. Right, so you don't have to worry too much. Okay. This is a photo of the sun taken with neutrinos. So it's not by our experiment, it's by a different one. But it's a pretty cool picture all the same. So that's what the neutrino, that the sun looks like if you look at it through neutrinos. Thank you.